In this work, we present L2G-NeRF, a local-to-global registration method for bundle-adjusting neural radiance fields. It integrates local and global alignment methods to simultaneously reconstruct the neural fields from RGB images and register the camera frames. Our model has two main branches. Based on query coordinates X and frame-dependent embeddings L, a warp neural field constructs pixel-wise local transformations T, and transforms query coordinates into a global coordinate system. Then the color can be rendered through a neural field to minimize the photometric error between renderings and images. In the second branch, a differentiable parameter estimation solver produces frame-wise global transformations T* condition on the pixel-wise correspondences. The query coordinates X are then transformed by the T* to apply a global geometric constraint. We first unfold the validation of L2G-NeRF in baselines, on 2D neural image alignment experiments. We use the image of girl with a pearl earring for the rigid image alignment experiment. As shown here, given color-coded image patches generated with random rigid perturbations, we jointly find the alignment in the top row, and learn the neural field of the entire image in the bottom row. We evaluate our proposed method against a bundle-adjusting extension of the naive 2D neural field, dubbed as naive. And another baseline is the current state-of-the-art BARF, which employs a course-defined strategy for registration. Alignment with naive leads to ghosting artifacts in the recovered neural image, due to large misalignment, while alignment with BARF improves registration results, but still falls into the suboptimal solutions. And thus struggles with image reconstruction. As L2G-NeRF discovers the precise geometric warps of all patches, we can optimize the neural image with high fidelity. We then use the representative images of the cat from ImageNet for the homography image alignment experiment. As shown here, alignment with naive and BARF still falls into the suboptimal solutions. On the other hand, we also evaluate our proposed L2G-NeRF against an ablation that builds upon our full model, by eliminating the global alignment objective. Note that the ablation is equivalent to a local registration method, and BARF is the chosen representative global registration method. Here, we zoom in to see the artifacts in cat ears. This indicates that global parametric alignment is susceptible to suboptimal solutions if poorly initialized, while local non-parametric alignment can minimize photometric errors, but does not obey the geometric constraint, which results in distorted artifacts. These two image alignment experiments demonstrate the general advantage of local to global registration, for both rigid and homography registration for 2D neural fields, which can be easily extended to other geometric transformations. We then investigate the problem of learning 3D neural radiance fields, from imperfect camera poses with synthetic object-centric scenes. Here we visualize the expected depth through ray compositing at the top, the image synthesis in the middle, and optimized camera poses at the bottom. We evaluate L2G-NeRF against a naive extension of the original NeRF model that jointly optimizes poses, dubbed as naive, and the course-defined registration BARF model. We can see that L2G-NeRF achieves near-perfect registration, and comparable visual quality to the reference NeRF trained under ground truth camera poses, while naive suffers from suboptimal registration and results in artifacts. BARF is able to recover a part of the pose misalignment, and produce plausible reconstructions. However, it still suffers from blur artifacts like the fog effect around the objects. This fog effect is the consequence of BARF's attempt to reconstruct the scenes with half-baked registration. To analyze the convergence of joint optimization, we linearly increase the noise by a factor of NC on the ship scene. As shown here, BARF fails to converge as NC equals 4, while L2G-NeRF fails to converge as NC equals 8. It demonstrates that L2G-NeRF is twice more robust as BARF. We take one more step to experiment with images captured using an iPhone under hierarchical camera poses. The results remarkably demonstrate the advantage of L2G-NeRF in registering images captured under large displacements, while BARF exhibits artifacts on the novel views due to unreliable camera pose registration. Here we show the experiment on images captured under sparse views, where the BARF exhibits ghosting on the renderings. Moreover, the difficulty of recovering pose from sparse views prevents SFM from finding accurate poses, which results in broken stripes on the synthesis of reference NeRF trained under SFM poses. This further demonstrates the effectiveness of removing the requirement of precomputed camera poses from SFM. Thanks for your watching.